Hello everyone. In this presentation, we will talk through the logic of our Python notebook and explain how each part of our code improves prediction accuracy for long defaults. Our goal was to build a systematic workflow that generalizes well on unseen data. Our evaluation metric is the F1 score, making the balance between preprocessing and recall our primary objective. The notebook begins by loading the dataset using pandas. We inspected the dataset shape, previewed the column, and identified our target variables, the long status. During the exploration, we observed the target is highly imbalanced. The vast majority of applicants pay back their loans while only a small fraction default. This observation directly influences our modeling decisions, as standard models tend to ignore the minority class if this imbalance isn't addressed. Next, we apply domain knowledge to engineer new features. Instead of using real data, we first handle the extreme outliers, capping applicants' age and employment experience to logical maximum to prevent bad tree splits. We then created financial ratios like loan to income, income per age, and credit history to age, because banks evaluate proportion rather than just absolute numbers. We also add some high risk flags for applicants with high interest rates and heavy loan burdens. This allows the model to easily isolate high risk groups. For preprocessing, we handled text-based categorical variable like gender, home ownership, and education level. We used one-hot encoding to convert this into a numerical format suitable for machine learning algorithm. To prevent feature mismatch errors, we align the test and training dataset columns, filling any missing columns with zeros. And dealing with the imbalanced target was a critical design decision. Initially, we considered using SMOTE to generate synthetic default cases, but this can introduce noise and cause overfitting. Instead, we use the algorithm native class weighting capability by passing the ratio of negative to positive cases directly into our model. We force the algorithm to heavily penalize mistakes on the real default class while keeping the training data pure. Next, before moving to complex ensembles, we evaluate baseline classifiers like random forest for diagnostic purpose. While highly stable, it was a bit too slow, and couldn't push our F1 score high enough. However, it confirmed that nonlinear tree-based models perform well on this dataset, justifying our transition to advanced gradient boosting method.
So next part is boosting models: XGBoost, LightGBM, and CatBoost. We then introduced three powerful boosting algorithms, which builds trees sequentially to correct previous mistakes. We selected XGBoost as a reliable, strong learner, LightGBM for its efficiency and uniquely wise growth, and CatBoost for its symmetric trees that handle data patterns differently. For all three, we set conservative hyperparameters, like lower learning rates and restricted tree depth to prevent overfitting. Next part is cross-validation and OOF predictions. To evaluate our model reliably, we implemented five-fold stratified cross-validation. This ensured the ratio of defaulters remained consistent across every data split. Instead of a simple train test split, we generated auto-fold predictions. This means every application's default probability was calculated by a model that didn't train on their specific role. This provides a highly realistic estimate of cargo test performance and prevents data leakage. Next part is ensemble strategy. Because XGBoost, LightGBM, and CatBoost capture different data structures, combining them reduces variance. Rather than simply averaging their predictions, we used an automated grid search to find the optimal voting weights based on the OOF predictions. This soft voting ensemble approach maximized the strength of each algorithm, making the final prediction incredibly robust. Next part is model diagonals and threshold tuning. Next came crucial steps for maximizing the F1 score, decision threshold tuning. By default, models predict a default if the probability is over 50%. However, a false negative is far more expensive than a false positive. We tested various thresholds and found that lowering it around 0.35 optimized our F1 score. We also reviewed the confusion matrix and the learning curves to ensure a healthy bias-variance balance, confirming our improvements weren't accidental. Next part is final model selection and submission. After finding the optimal ensemble weights and decision threshold on the validation data, we applied this exact logic to the unseen test set. We combined the probability predictions from all three models using our learned weights, applied our adjusted threshold, and formatted the final binary predictions into the required CSV submission file. The conclusion, in summary, our notebook follows a structured progression from data exploration and feature engineering to robust ensembling, strict cross-validation, and strategic threshold tuning. Each decision was designed to prevent data leakage, handle class imbalance, and align model outputs with real-world business risks. This workflow allows us to develop a highly accurate and stable classification model. Thank you.